Okay, so for today, we're going to just real quick review exponential population growth and logistical population growth, and then just look at a couple of practice questions on things you might see and how to actually solve for them. Then we'll start talking about population density, and I'll have a little bit of reading for you on that, also linked right below the video on Classroom. So, exponential population growth. We know it by the graph because it exponentially is growing, right? That population shows no signs of shrinking, plateauing. It keeps going up. This was our formula for exponential growth. So we have that change in size over change in time equals the maximum growth rate times the population size. So a lot of this looks similar to the things we saw in the calculations from yesterday. The one thing I want to point out is this dn over dt. Remember, that is equal to the b minus d, birth rate minus death rate. So if we know this information, the birth rate and death rate, we can figure out dn and dt, which can then be just plugged in to this equation. So we don't always need the change in time or the change in population size to solve for this, as long as we know the birth rate and the death rate. Logistical growth looked a little bit different, but the graph started the same way, right? It has a sharp increase, but then it starts to level off somewhere, right? It hits that carrying capacity, which means there's no longer enough resources available in the ecosystem, in the environment, to support any more individuals in the population. So we typically see, right, it gets to that carrying capacity, then this population would decrease as the resources get used up. Once those resources start to come back, the population will start to come back, and it kind of makes this continuous wave-like pattern here at the top. Of course, there are other things that can affect this, but we're just going to look at it as far as resource availability actually goes. The formula for logistical growth is the same as exponential growth. The only difference is that for logistical growth, we have to factor in that carrying capacity, right? So that's K, that's my variable. So how many individuals can the ecosystem actually hold? But otherwise, they look pretty similar right there. So if we look at an example of each of those, the math is not too bad, right? Just like the math you did yesterday. So here's my question for exponential growth. There's a population of 2,500 mice in a field. The population is experiencing exponential growth and is producing 500 offspring each month. So that's my birth rate. On top of this, 75 of the mice are dying each month. So there's my death rate. What is the exponential growth rate of the population? So I'm going to use both of these equations a little bit because we don't know dn over dt, right? Well, we could figure out the change in population size and the change in time, but we were given the birth rate and the death rate in the equation, 500 minus 75, right? If I do 500 minus 75, I get 425. So this dn over dt is equal to 425. Now I can start plugging things into my formula down here, right? You can kind of see it is worked through a little bit more over here. So we have 425 on this side. We're trying to find this R max. My value of n is my total population size, which is 2,500. So I'm going to divide both sides by that 2,500. So my final answer is 425 divided by 2,500, and I get 0.17. I would recommend writing this one out so you get the idea of it. But again, all we did was did the birth rate minus the death rate. That gave me this value on this side of the equation. And then I plugged in the number I was given for the population size for n. Then it was just a matter of solving for r, right? Just kind of like a basic algebra equation. But that is exponential growth. Logistical growth, like I said, same kind of steps. There's just that extra carrying capacity that we have to factor in. So in a population of birds, the birth rate is 225 per month, the death rate is 150 per month, the carrying capacity for the area is 275 birds. What is the logistical growth of the population if the initial population size is 150? So same thing, I'm just going to plug that information into this formula. We know that dn divided by dt is equivalent to the birth rate minus the death rate, which we were given up here, right? So 225 minus 150. And that equals that R value, which is what we're looking for, times the population size times the carrying capacity minus the population size divided by the carrying capacity. So it's just putting all these numbers in their correct spot, right? And that's what this top line over here is. So here's that birth rate minus the death rate, which is equal to this right here. Then we have that R value times the N, which is the initial population size, times the carrying capacity minus the population size divided by the carrying capacity. If we were to plug that in, we would get something more simplified like this, right? So 75, so 225 minus 150, give me 75. If I multiply these numbers out, I get 68.2. So then I just have to divide each side by 68.2, and I get R equaling 1.1. So my logistical growth value is 1.1. Those questions, most of the time you're just given the information, and it's all about just plugging it into these formulas. Like I think I mentioned in my last video, both of these formulas, as well as this one we talked about the other day, are provided for you on your AP equation sheets. You do not have to memorize them. Those will be provided to you. Moving on a little bit, now we want to look at density, right? We've looked at growth. Now we want to look at how does that affect the density of a certain population. So population density is just how close individuals in a population actually live near one another or to one another. When there's an abundance of resources, the population becomes very dense, and the problem there is that means there's limited space, right? I have a lot of organisms, a lot of individuals in a very potentially small area. Here's the population density of the U.S., right? And obviously this has a lot to do with those big cities, because we tend to see denser populations in big cities. But that kind of relates here because those cities usually have an abundance of resources, right? They have lots of jobs, they have lots of stores, they have lots of life there. So other people tend to flock towards those areas. That is our map of our population density. Limits to population growth and density are due to many factors. So we have density-dependent factors and density-independent factors. So what can alter the density of a certain population, right? So density-dependent factors are things like competition, disease, predation, territoriality. So these are all dependent on how dense that area is, right? Areas that are more dense are going to have higher rates of disease, more competition, more predation. So they're going to have more predators in the area. Whereas less dense areas, this stuff might not be as big of an issue. So these factors are completely dependent on how dense is the actual population. But obviously, if I have a dense population and we get disease, that density is going to start to decrease. So that's how it affects that density. Our density-independent factors are those factors that are going to affect a population regardless of how dense it is. So this is more things like natural disasters, pollution, right? So think of it, regardless if I have a small or low density population and a high density population, if there's a tornado that rips through there, that population is going to take a hit either way. When those dense populations exceed the ecosystem resource availability, that's where we get that logistical growth value, right? It reaches a point and then we see it kind of wavering off at the top there because it can't support too much more. So density is why we have this. It can't be too dense, otherwise we're going to see the death rate start to increase because of those lack of resources. There is a little reading on density and how we can actually try to survey density and figure out how dense an area is. I want you to go ahead and read that, and that will be your work for this Friday.